So I think we started with D21 as one of the options. And so I'm just going straight to the this section of our spreadsheet. I kind of do a shorthand to get to this. But basically at this point where we're at, you've got a peak at 107, one at 281. There can be potential dropout with either of these peaks. Even though 281, the 30 alleles at 281 is above your stochastic threshold, again, that stochastic threshold is based on a single source sample. So based on peak height sharing, let's say you have, a 1-to-1-ish type mixture, or maybe a little bit more than that. You can take a portion of that 29 that can actually pair. I mean, that could actually pair with something all the way up to 300-ish. But even if you say it pairs with something at 200 or 180, the amount of that peak of the 30 peak remaining is going to be under your stochastic threshold. And so you could have dropout associated with that 30. And that's one of the things you always have to keep in mind is just because you do have a peak above stochastic threshold, if it's in a mixture, you need to look at it because it still could be associated with dropout. So in this case, we would do a 29X and a 30X, or if I was in other parts of the world, I'd do 29F, 30F. And so that accounts for that 29 paired with itself or paired with anything else, any other allele. Same thing with the 30. It's a 30-30 or 30 paired with any other allele. Now the problem with that is, and that's where you get into, let me just grab this pen. Got it. That's what I've notated down here. If you have two X's, a 29X and a 30X, you actually have duplication of the 2930 because you've got the 2930 based on the 29X and you've got the 2930 based on the 30X. So, this isn't absolutely necessary, but if you want to get a little bit better representation, you need to subtract out one of those 2930s. And that's what this is down here. So we're just subtracting out that extra 2PQ. And so you'd sum all this and you end up, including 72% of the population at this locus. So again, that's a pretty large percentage of the population that's a potential contributor. But at least now you're able to use this data, and you can exclude about 28% of the population.
Just real quick, do you ever get a situation like that where the frequency is greater than 1?
Yeah, I mean, because especially if let's say you have the two most common alleles, or let's say you have 3 alleles with 2P, and you end up having, you can end up summing this because you're not looking at just 3 people. When you start doing the 2P rule, you're actually looking at that allele associated with all the other allele frequencies. So you can get something greater than 1, but obviously the random match probability can't exceed 1. I mean, you're including people that don't exist. So you just pretty much cap it off. So once you get to 1, and once you go above that, you just cap it at 1.
So with this one, when there's only the 2 alleles that are observed and you're assuming 2 contributors, you're kind of making that leap of faith that at least 1 allele from the 2 contributors was detected here?
Yes.
At what point do you not, like how low do the peaks have to get, and yet still two peaks present, that you're not confident that 1 contributor hasn't completely dropped out?
Well, again, looking at the overall profile, what you're thinking that the general mixture balance would be. I mean, it kind of comes down. There's a lot of factors that go into that, but at this point, I felt fairly confident that I thought both components were being represented there at least partially. If I didn't, then yeah, I would just drop this locus.
So you don't have an absolute cutoff, though, if the peak heights aren't? Because
there's too many things that start getting involved. I mean, I think I'm going to talk about this a little bit later, but if you start trying to create absolute limits, you say, okay, well, based on a quant or based on certain peak heights across the board, what happens if you've got a pristine component and a degraded component? Now things start getting more gray of, even though it may fit within that category at most loci, at the larger molecular weight loci, you're not going to be comfortable that it's actually present. Or the reverse of that, you may say, well, based on this stuff, I don't think everything's present, but at the small molecular weight loci, you might be confident that they are. So it's just more of putting out guidelines, a framework that you can work within, and then hope, training experience, et cetera, are on your side. And then you should, we always try to fall back on the conservative side of things. That's one of the things, we talked about training, how you have consistency, and we're a fairly small lab, but we implemented this, I don't know, probably 3-4 months ago at this point. And so we get together on a bi-weekly basis, and we bring in, ugly mixtures, and we sit down for 2 or 3 hours and just hash these things out and beat on each other for, 2 or 3 hours. And I, initially said we're going to have these bi-weekly meetings. It's just going to be a half-hour thing. I don't want to waste everybody's time. The first one lasted, I think, 3 or 4 hours, and it's been pretty much that every time. So just me and my pulpit. So D2. Again, looking at this with 3 alleles, assuming it's a 2-person mixture, I'm fairly confident that this is a 2-person, or I have at least partial representation of both components of the mixture. But again, because of where they are, I went with 2p for each of the alleles. So you've got the 17x, the 22x, and the 23x. But again, since you've got multiple 2p rules going on, and we actually use 2p minus p squared, but I'm just calling it 2p, you've got to subtract out the different overlaps. So you're going to have, that's what up here, this first one is 2pq for the 1722. This is 2pq for 1723, and then 2pq for 2223. So then you sum all that up, and you're at this point you're including about 56% of the population. So again, I mean, still pretty big numbers, but it's better than not using the locus at all. FGA. This is one that, again, we would not include that, obviously, that peak that's below the analytical threshold. Obviously, it's there, but we're not including that as a potential allelic peak. But it does substantiate the thought that, potentially there's allele dropout associated with this. We have 3 called peaks. They're all below our stochastic. They're all low level. So again, we went with 2p rule for all these. So you've got the 18x, the 22x, and the 24x. And then you've got these 3 subtractions to get rid of the duplicate 2pqs. And then you end up with about 62% of the population would be included. We good? Sweet.
Todd, can I ask you a question? Sorry, you thought you were done. Can I ask you a question? On this same profile, and I don't use this particular multiplex, but there's a locus that is only registering a 15 allele, but there are 2 alleles that must have been under the allelic threshold. Can anybody tell me what, it's at 119? I don't know what locus that is. D3? Thank you. If you had a suspect that had 2 alleles that matched those 2 peaks underneath that allelic threshold, would you include that suspect, or would you eliminate that suspect, assuming his other alleles are falling either under that stochastic threshold or matching the alleles that you see?
Well, we would have formed our interpretation before looking at any references. And so we would have looked at that and said, okay, I've got a 15 at 119. I know this is a 2-person mixture. I'm making the assumption it's a 2-person mixture. I don't feel like I've got complete, at least partial representation of both components. So therefore, a contributor to this profile may not be represented by that 15 at all. So I could have an 18, 20, a 23, 24. Actually, that's not really an option, but you could have anything else. So you could have complete genotype dropout. So I wouldn't use this locus for comparison purposes because it's anyone's.
Would you use it for statistics, and if so, what would you be using that dropout factor again?
No, and we wouldn't use this for comparison or statistical purposes because essentially, if you can have complete genotype dropout, anyone's a potential contributor at that locus.
Okay. Thank you.
Thanks, Mike. Mike's a real whiz with this technology. It's fantastic. I really want to tackle this particular locus, the FJ locus, and I've got a few questions really of you in the first instance. It's low level, we know it's low level. This is the only locus in this profile, as I can see, that's got 4 alleles represented. Would people agree with that? Anybody dissent? Can I ask you a question? Okay, we've got one, our 24 allele is at 50 RFU. What's the 23? I don't know, it's not been scored, what, 49? So is it suddenly doesn't exist because it's at 48 or 49 when the 50 has been scored? Or do you apply your thresholds absolutely in situations like this? Absolutely. Okay. That's interesting.
If you define a floor below which you can't be confident that it's not noise, you can't move below that floor.
Okay. But would you accept I have got a significant peak at that point? Okay. And it's significantly above your noise level? Okay. So the question is whether that's an allele or not. But anyway, that's, I mean, I'd be happy to accept it. There we go. So we've got a person of interest in this instance of a 2324. So again, we go right back to the basics. So likelihood ratio equals what in this instance? POI plus unknown over 2 unknowns. Yeah. Everybody happy with that? So in this instance, my 24 is represented in my person of interest. I'd be happy to accept the 23, but I'll take your point. So I've got to account on my top line for the 18 and the 24. Okay. Now, given we're not going to have that peak at 23, are we confident we've got full representation of a 2-person mixture? Then you've got to say no, and we've got to invoke an F, a missing. Sorry, I'm looking at the wrong thing. I beg your pardon. It's we've got the 24 in, so it's you're right. Here am I. I've got to account for the 22. I'm glad some of us are awake. Okay. So I'm going to invoke a missing allele, an F. Everybody happy with that for the bottom line? And I've got to account for 2 contributors or 4 alleles. So we've got an 18, a 22, a 24, and something else. Everybody happy with that? I'm not putting any numbers in at the moment. On the top line, I'm going to have 2 factorial over 1 factorial times 1 factorial, which is 2. Okay? And on the bottom line, I'm going to have 4 factorial over 1 factorial, 1 factorial, 1 factorial, 1 factorial, which is 24. Everybody happy with that one? Okay, which is going to give me 2F18, F22 over 24 F18. Take that mark away. F22. I've got the F goes, of course. F24, which comes out as 1 over 12 F24. To 12, 18, 22 goes 1 over. Okay with that one? Have I thrown away any information? I mean, I think I've thrown away information. I think I've thrown away the fact I've got a 23. But, you know, are we going to differ on that one? Or?
How did we get rid of the F?
Oh, sorry, when you, this is the John's mathematics from earlier in the week, where when we put the factorial figures in, we can get rid of the F's. We just delete the F. We've taken account of it.
You want to know the logic for it? F is any allele at all, so the frequency of F is 1.
That's why with CPE I said 1, 1, 1, because you would include anything, all alleles, everything's possible. So it sums up to be 1.
I think if you know, you would accept that we got a 23 there, we'd have a different we'd have a different answer at the bottom. I think we'd have 1 over 12F 23 24. Mike, I'll leave you.
Sorry. Okay. Todd actually has one other example that he wanted to show as sort of a real-world example.
Kind of doing this as a quick break between the homework stuff and then the more complex mixtures we're going to get to, which I think will probably be after lunch. As we're sitting here, I was thinking of the recent Charlie Sheen things, and I have a whole new perspective on one of his quotes. He kept saying he was F-18 baby. I was thinking he was referring to the fighter jet, the very fast jet, things like that. He's actually just talking about the 18 allele, the frequency of the 18 allele. That's much better. It's on your thumb drive. Wrong thumb drive. Okay, just do this. So this kind of stems from some of the conversations we were having out in the hallway and during some presentations, but a lot of the validation studies we do and a lot of things we look at are pristine. We're all told to do mixture studies. So we all do the 1 to 1, 1 to 2, 1 to 5, 1 to 10, 1 to 20, and 20 to 1, blah, blah, blah. But we usually do it with just pristine data, so or pristine samples. We've got pristine source DNA mixed with pristine DNA, and you kind of get it together and you get this nice pretty thing. And then you run into your first case and it's something that's been sitting outside, or you've got an old t-shirt that has blood on top, so you've got this pristine DNA mixed with a degraded DNA sample. And things kind of get a little bit more interesting then, because now all of a sudden something that's a major contributor at the small molecular weight starts to fade off, but yet the potentially the more pristine data stays somewhat constant throughout. And so where do you know when those things actually cross, if they do cross? And so this was something, part of our validation study, because we knew we were going to be working with crap data. We did the recommended validation studies with mixtures where we did pristine with pristine, but then we took pristine DNA and mixed it with degraded DNA. And we did moderately degraded and then also severely degraded, and did the same type of things just to see kind of what happens. And so theoretically, yep. Thank you. Sorry about that. So again, this is just a degraded major. So you've got the major component. Theoretically, this is I believe a 5 to 1 mixture, but the major component is degraded and the minor component is fairly pristine. So this is the blue channel. This is the identifier, 28 cycles. And so you kind of see you've got something going on here. And I'm just going to go through, we're going to look at this more in depth, but just kind of get a general overview of what this profile looks like. You get down here, you kind of see something going on, but you can kind of potentially think that, okay, you've got a major component here. Don't know. Start working down, now you're closer to a 1-to-1, maybe 1-to-1-ish, who knows what. But then down here you just have 2 alleles. And without thinking that this may be, you know, a degraded sample, you might think that when you get down here, this is the major component that's just kind of gotten a little bit low because it's the high molecular weight. This got a little bit cramped, so I kind of broke it up. But you see, again, you've got, you know, this fairly major going down. It gets kind of 1-to-1, then a little bit less, and then down at the end, you only have 2 alleles that are detected. This one is below the analytical threshold. Same thing going on here. Start going down. This is actually a mixture of two males. But you go down, and again, you're seeing the ski slope effect, but with FGA, that's not unusual anyways. So then I went through and kind of knowing what the actual components are, started looking at what are the contributors here. And so the green triangles represent the major component. The red triangles are the minor component, the alleged minor component. And they're kind of stacked where there's a shared allele. So you look at D8, this first one, you've got, you know, I'm basing it pretty close to a 50-50 peak balance, or a 100% peak balance here. So you see you've got your major and minor, which is already almost looking like almost a 1-to-1 ratio, even at D8, even though this really is, it was 5-to-1. But because the degraded DNA just wasn't amping as well, obviously it's going to cut down on that. You look at whatever the next one, D21, you start seeing it come down. The same thing. I broke it up to make it a little bit easier to see, but I just wanted to use the actual electropherograms at first. So then I basically went and I measured the red peaks, measured the green peaks, made them bars, and then stacked them so it was just represented as a single peak. So at D8, this locus, you're already at almost a 1-to-1 mixture. You see D21, you've got a little bit more of the major components actually still coming through a little bit. But then you get to that one, D7. Now you've got the minor component is all of a sudden showing up as the major component in this mixture. But then you look at CSF, they're back to 1-to-1. And this kind of gets into how DNA gets degraded. We used UV light to do this. It was easy. I don't like putting nucleases in our lab, so we knew UV light would do what we needed to do just to show what we were trying to show. D7 drops out almost instantly as soon as you expose it to UV light. And we were doing some DNA repair work, and we saw that, you know, when we hit it with the repair enzymes, it would pop right back up again. It would go from complete dropout to back up to 300 or 400 RFU. So D7 obviously has a thymine stretch somewhere, either in the prime region, the flanking region, wherever, but it obviously gets affected by UV light worse than anything else. And this isn't unusual. I mean, you don't always get a ski slope effect, but I'm not even going to get into that. Whole different world. So I just thought this was interesting. If you look at D7, how, you know, that major component, which is the one that's degraded with UV light, takes a big dip at D7, but it comes back up at CSF. So you look at the next series, you've got D3. Here at D3, the major component is actually looking like a major component. You look at the next looks horrible at this. I'm not good at memorization. Though starts looking a little bit closer 1-to-1. Look at D13. It's looking a little bit more, maybe 2-to-1-ish, with the minor component starting to take over. But you get down here, and you've got these 2 alleles that are showing up. What's actually showing up at the bottom end of this, or the higher molecular weight, is actually the minor component. The major component, you know, the alleged major component is completely dropped out at this point. And so you start seeing, you know, if you've got this degraded, the major component, which is degraded, is following this ski slope type of thing. The minor component, which isn't degraded, is staying somewhat close to straight across. And the problem comes in during your interpretation is you're not going to know. I mean, obviously I knew what the components were going into this, but when you're looking at the actual profile, you don't know when they cross. And so you start getting into this kind of gray area of how far out are you going to go down the ski slope where you're still confident that the major component is the major component at that. Yes, Steve? Please.
See, with looking at a profile like that, I would not have been tempted to interpret it as a major minor because I'm seeing loci where I'm a lot closer to 1-to-1.
Right.
Do you see profiles where I wouldn't have that warning and the crossover would come without going through an intermediate area where I would not be comfortable separating out a major and minor at all?
Short answer, yeah. I mean, it really depends. I mean,
So
at
you
the
see
low
ones
level.
you see ones that flip pretty suddenly without seeing an intermediate area where they're closer to 1-to-1.
Yeah, I mean, you can go from pretty much D8, D3, D5, and D19, where you've got a pretty clear major, and then you go to the next locus, and some of those loci are already starting to flip. And you can, I think it was,
But I mean, would you ever see a profile where there's a complete absence of loci where you'd be warned because the proportions are getting a lot closer to 1-to-1?
I don't think so.
I mean, it doesn't seem, that's why it doesn't seem very dangerous to me, because I would never have been tempted to separate that into major and minor in the first place because of that.
Yeah, well, I mean, the problem is, at some of these loci, and this is a little bit more extreme example, but there are examples where, you know, I think this is a 5-to-1, but you can look at 10-to-1, some other issues where at D3, you would feel very comfortable saying this is a major component. Then once it gets down to this range, you're not really sure what's going on. Some of these things, you may have complete genotype dropout. Who knows? But maybe at, you know, the next locus, you're not quite sure. And so what we've done in the past is just pull out D8, D3, D19, and D5, where we're very confident that because you see this degradation occurring, that at the small molecular weight loci, we feel very comfortable that the major component there is the same at all those loci. But once you get past that, we have no idea what's going on. And so we'll just pull those off as the major component and pretty much chuck the rest. So again, going to this or this channel, same type of thing. You've got the major component kind of degrading. You've got the minor component. Pretty much at the next locus, it's almost a 1-to-1, and then it goes downhill for that, from there. So the minor component's taking over. And here again, even at D5, if you've got something where it's a 1-to-1, but you've got absolutely no representation at FGA of the major components completely dropped out. So we just wanted to throw that up there. There's been some questions, some discussion about it, so we wanted to throw that up there. It's just a quick discussion point.
Okay, so I was hoping that either we would have more time in this morning session to get into the next 3 examples that we have, are the ones that are more complex, but we're also getting close to lunchtime. So I think maybe if we could take about 10 minutes or so, if anyone has any questions or comments or any questions for John or Chris or Todd, anyone, feel free now to take that time before we break for lunch, and then after lunch we'll concentrate on the 3 complex mixtures. Does anyone have any questions? Everyone over here.
Todd, do you know what your initial concentration was on that last example?
No. We did it with quantifiler, so who knows? But it was, theoretically, total input was around 200 picograms. But at that level, we were aiming for 200. Oh, sorry, no. Sorry for this. That was a different thing. It was, theoretically, it was closer to between 800 and 800 picograms and 1 nanogram.
I think it would be beneficial maybe for the 50-50 mixture, for example, given the allele frequencies that we were provided with, to see kind of side by side what the results of each of the different calculations are in the end, so that we can get an idea of what the final numbers that would be reported for each of those would be.
That's an excellent question. In fact, Todd just said, hey, how about during lunch we put the numbers together and side by side, and we'll show before we get started. So yeah, we actually thought about that just to show what information is lost and what information is gained by looking at the different statistical approaches. So yeah, we'll do that.
If you're using the CPE for an unresolved mixture, how do you resolve or defend the fact that the individuals may not be from the same race?
So it's a very good question. So how do we resolve that the individual may not be of the same race? I think the one way to work around that is to calculate with the different frequencies for the different groups. Maybe one way, but that is a difficult question where you have, suppose, one individual who's Caucasian, one individual who is African American, and you're then just taking the Caucasian allele frequency. So I don't know if there's a really good answer. John, do you have a comment? Put him on the spot.
You know, thank you guys, and Debbie snuck over here with a microphone to set me up for this as well. I don't know why I'm being asked to defend CPE. I must be one of its largest protagonists, mustn't I? But look, what's the question? The question is the chance that one person is excluded from this, you know, a random person is excluded. So you can do that calculation for each race, right? So it's perfectly straightforward. You can do it for each of your 3 ethnic groups if you choose. But look, maybe we need to go back to just exactly what CPE purports to be. It purports to be the chance that a person selected at random would be excluded from this mixture. Not 2 people, a person, right? So, so that a person could be from any of the racial groups, and you can do a number of calculations. I mean, I really don't want to get there because for me it's an artificial statistic. So I don't want to defend it too much, but you can certainly do it 3 times. 4 times, yeah.
It also assumes that the individuals are unrelated, which, as we heard yesterday, that often you have, you know, families that are into crime that you may have 2 brothers, say, that are in the stain. So there are a lot of assumptions you're making about using CPE that may or may not be truly justified. Any other questions? Okay, I'm going to, I guess, turn it over to Debbie for a couple of announcements, and like I said, after lunch we will continue on with the complex mixtures.